Hey guys, this is Mrs. Mooney, and we're going to do Lesson 16, Session 1. We're going to use functions to model linear relationships. So we've already looked at what is a function and what a function doesn't look like. And we've also distinguished between linear and nonlinear functions. So now we're going to look at how do we use a graph or a table of values or an equation to model a real world situation that is a function. So we're going to use what we know to try to solve this problem about pizza. A customer can use the menu above, that's this menu right here, to call in a pizza order. He or she chooses a size and then adds toppings. These graphs and equations model the prices of the two sizes of pizza. Okay, so we have two equations and we have two graphs over here. Each one of them models either a small pizza or a large pizza. And we have to figure out which equation and which line model the price of the small pizza and which equation and line model the price of the large pizza. I'd like you to pause the video and see if you can figure that out from the information given in the menu. All right, so let's start with the small pizza. I'm going to go back to the menu and look at the information I'm given for a small pizza. It looks like a small pizza with no toppings starts at $8. So that's my starting price. And then every topping I add is going to add another $1.50 to my total cost. Okay, so again, this is my starting value. I'm looking for a y-intercept or a b of 8. And I'm looking for a rate of change of $1.50. So it looks like this first equation has a y-intercept or a b value of 8, and it looks like I have a rate of change of 1.5. So that looks like it is the equation of my small pizza. So I'm going to write small here, and then I'm going to go over to the graph, and I'm going to look for a y-intercept of 8 and a slope of 1.5. So on my graph, it looks like this pink one crosses the y-axis at a y value of 8. That's my starting price. And let's find another point so that we can find the slope of this line. So between these 2 points, the y-intercept and this point here, it looks like my rise, be careful because the scale of this graph is a little different. It looks like I'm going up by 2. So I'm going up 2, 4, 6. And it looks like on the x-axis, we're going over by 1. So 1, 2, 3, 4. So my rise over my run is 6 over 4. That's equivalent to 3 over 2 or 1.5. All right. So this is, in fact, the graph of this equation right here. Y equals 1.5x plus 8. So then the rest of this is sort of elementary, right? It looks like, let me erase this, clean this up a little bit. So if the first equation is my small pizza and the pink line is my small pizza, then that means that this equation must be my large pizza and this line must be my large pizza. Let's just verify. So the large pizza, it looks like before I add any toppings, it's going to start at $12. And for every topping I add, it's going to cost me another $2. So I'm looking for a starting value, a B of 12. And I'm looking for a rate of change of $2 for every extra topping X. All right, so this one fits that bill. It starts at 12 and it has a rate of change of 2. Let's check the graph over here. It also starts at 12, and let's find another good point so we can find our slope. So my rise is 2, 4, 6, and my run is 1, 2, 3. So 6 over 3, that's equivalent to 2. So this graph starts at 12 and has a rate of change of 2. Same thing that I have in this equation. All right, so I'm going to clean this up. And what I'd like you to have in your books is I would like you to label each of the equations and each of the lines. Is it the small pizza or is it the large pizza? Both equations, small or large, and both graphs. I want you to write, is this the small or the large? Pause the video, write that down, and then come back and check your work. Okay, so this is what you should have got. And now I would like you to go down to the bottom of the page in the try it. And I'd like you to answer this question in the discuss it. Which numbers in the problem helped you answer the questions? So you might need to go back up to that menu and talk about which of these numbers in the menu helped you helped you determine which equation fit the small pie and the large pie, and which numbers helped you find the correct graph to match the situation. Pause the video and come back and check your work. Okay, so the big pieces of information that are really key are those starting costs, right? That starting cost of the small pie goes right here in my equation. That's my B, that's my y-intercept. And my cost per topping, that's my rate of change. How much does my total cost change per topping? That's $1.50. And that goes right here into the slope of my equation. And same thing with the large pie. My starting cost for the large pie is $12. That's my y-intercept or my B value. And my cost per topping, that's my rate of change. How much does my cost change for each topping that I add? Okay, let's move on and start making some connections on the next page. In connected number 1, you're asked to look back at that try it problem. And you're asked which equation and graph represent the price of each size pizza, and how do you know? And we just answered all of that previously, so I'm not going to write anything in my book, but I want you to make sure that you write in your book which equation is the small pie, which equation is the large, and which line, blue or pink, is small and large, and how do you know? So talk about what numbers and what parts of the y equals mx plus b equation connect to those numbers, right? So remember y equals mx plus b. So talk about rates of change, and talk about initial values. Okay, in the look ahead, we are being asked, we're talking about the graphs and equations back in the try it problem. Those are linear models because they model or represent linear functions. In part A, a linear function has a constant rate of change. We talked about that in class. That's what makes it linear. What do the rates of change represent in this situation, in the try it problem, in the pizza problem? Well, let's go back and look. Again, the question is, what do the rates of change represent in this situation? So let's go back and find our rates of change. Okay, so we're looking at we're looking at 1.5 and we're looking at 2. So I want you to remember that the rate of change or the slope is equal to the rise over the run. If you ever forget, or if you ever are asked to interpret your rate of change, look at which axis represents rise. Well, that's price. So I could rewrite this as price over, and which axis represents run, or what's represented on that axis? The number of toppings. So price over number of toppings. So we're going to use this to interpret this 1.5 slope for the small pizza, or rate of change, and this slope of 2, or rate of change of 2, for the large pizza. So let's go back down and use this information to answer the question at hand here. Okay, so again, what we looked at up above was, what is that change in price? How is price being affected or changed by changes in the number of toppings? All right, so the rates, again, for the small pizza are 1.5. So my change in price per change in number of toppings is 1.5, or 1.5 over 1. So my price changes by $1.50 every time I add one more topping. Now I want you to write that in your own words. What does that slope or rate of change for the small pizza represent? And then I want you to answer the same question for the large pizza. So I would say the price of the small pizza increases by $1.50 for each topping, or per topping. All right, and we can say the same thing, only using different numbers for the large pizza. So the price of the large pizza goes up by $2 every time I add a topping or per topping. So that's how we interpret those slopes. Okay, so now we're going to look at question B. The initial value of each function in the triad is the value of y when x is equal to 0. So what do the initial values represent in this situation? Let's go back and look. So our initial values are 8. Whoops. Our initial values are 8 and 12. Let's get rid of some of this other stuff here. All right. So if these are the values that y is equal to when x is equal to 0, well, what does that mean? So x, again, I'm going to erase some stuff over here. Let's get rid of this. So x is equal to the number of toppings. So when x is 0, that means I have no toppings. So then what is that initial value equal to? How can we make sense of that initial value? So pause the video for a second, think about that, and then come on back. Okay, so if we have 0 toppings, and at that time our cost is $8, then that must be the initial cost for a small pizza. Oh, that doesn't look good. Let's erase that. So that's our initial cost. And in fact, we could say the same thing for the y-intercept of the large pizza. That is when we have a number of 0 number of toppings, and that is the cost at 0 toppings. So that's the initial cost before you add any toppings. Let's scroll on back down to question 2, part B, and let's answer that question. So the initial value, what do the initial values represent in this situation? So for a small pizza, the initial value was $8. So small is $8 for no toppings, before you add any toppings, before toppings. And a large is $12. That was our y-intercept, before you add any toppings, or at 0 toppings, however you want to word that. Okay, so let's look at C. What quantities do the variables x and y represent in this situation? So let's stop here and answer this part of the question. Let's go back up. What do x and y represent? Well, let's look at the graph. The graph usually tells us exactly what x and y represent. Okay, so on the graph, we can see that on the x-axis, we have toppings. I actually don't like that. Is it the taste of the toppings? Is it the total cost of the toppings? No, it's just the number of toppings that we've added to the pizza, right? Number of toppings. And then, so that's x. And then y, well, what's on our y-axis? Well, it's price, right? Is it the price of each topping? Well, let's look closely here. It looks like we have y is set equal to all of this stuff, the initial value plus the 150 that we add for each additional topping. So y is our total cost of the pizza, given the number of toppings. So let's scroll on back down and record our answer here. All right, so we're going to answer the first part. X is equal to the number of toppings on our pizza, number of toppings, and y is equal to the total cost of a pizza, total cost of the pizza, given the number of toppings. Let's look at the next part of this question. So we're being asked to use the phrase is a function of to describe the relationship between these two quantities, the number of toppings and the total cost of our pizza. So remember how we thought about this in class. Thinking about is a function of is sort of clunky, and it's not really second nature to us. But if we replace is a function of with is dependent on, then we can figure out which one depends on the other, which one is a function of the other. So let me ask you a couple of questions. Does the number of toppings depend on the total cost of the pizza? Or does the total cost of the pizza depend upon how many toppings we added? I want you to take a second and think about that. Okay, so which one depends on the other? You should have gotten that the total cost of the pizza, the total cost is dependent upon how many toppings did we add. So the total cost is a function of the number of toppings. So remember, when asked a question like this, replace is a function of with is dependent upon. That'll really help you answer these questions. All right, one more question before we start practicing. So the reflect it question is important. I don't always do the reflect questions, but I think this one's really good. We're being asked to look back at the equations and the graphs in the try it problem, and then consider which type of these models, equations, graphs, would you rather use to find the price of a pizza? Because we all have different brains. We all think differently when we're using mathematics. So I want you to turn back to that page and decide which one do you prefer to use to analyze the situation and why. And when you're done doing that, I would like you to turn the page and complete the practice pages. There are 2 practice pages. So this one, I do want you to do this vocabulary. I think that's a good review. And then I want you to do this word problem on the following page and check your answer to problem 3A. When you're done, you can come back to this video and you can check your answers just to make sure that you did the problems correctly. All right, time to check your work. So you can pause the video so that you can look at what I have a little bit longer. Remember, you can go to the interactive glossary at the back of your textbook to find the definition of slope-intercept form of a line. You should have your own examples and non-examples here. Remember to find your y-intercept and your slope from the graph, and then simply plug them into the y equals mxb form of a line. For here, you'll need the information on the carnival poster. And you'll need to match that up not only with the equations, but also with what's happening in the graph, with the b values on the graph, as well as with the rise over run to find your slope. And finally, you need to match up the scenario with the equations. So we're looking for an initial cost for the adult tickets of $10. That's the admission fee, the entrance fee. And then for each ride, we're looking at a rate of change of 1.25 for adults. So for each additional ride, you add $1.25 to your cost. And similarly for children, our entrance fee is $5 and it's $75 for every additional ride. So this is our adult equation and this is our child equation for total cost. And then finally, one way to show your work, to check your work, is by finding the slope a different way. So instead of counting out the slope on the graph, you could use the slope formula, find 2 good points, subtract your y values in the numerator, and subtract your x values in the denominator. Make sure you do them in the same order so that you come up with the correct slope. So here's our rate of change. Our slope is our rate of change. That's 0.75. Well, we know child tickets are 75 cents each. So the pink line is the total cost of the child tickets. And this is the graph of y equals 0.75x plus 5. And then for the blue line, we're looking at a rate of change. Again, we use the slope formula to find this. Subtracted the y values and divided them by the x difference of the x values, and we got 125. And we know that adult tickets are $1.25 each. So the blue line represents adults, and the blue graph is the line matching this equation, y equals 1.25x plus 10. And that's it. I hope you guys have a great distance learning day, and I will see you in class.